Transformers are one of the most important and most misunderstood parts of the electrical system. We're not here to make you electrical engineers. By the end of this video, you'll have a rock-solid foundation of how they work and why they matter. At their core, transformers do two things. They step voltage up or they step voltage down. That basic function is what makes the entire power grid possible. For example, a generator at a power plant produces electricity typically between 11 and 25 kilovolts AC. That's not high enough to move efficiently over long distances. So we send it through a step-up transformer, which raises the voltage to hundreds of kilovolts. Higher voltage means lower current, and lower current means less energy lost as heat. On the other end, voltage has to be stepped back down to something usable. No one wants 500,000 volts running into their house or data center. That's why substations and distribution transformers step down the voltage gradually until it's safe for homes, businesses, and industrial sites. Before we go deeper, let's cover a few fundamentals. Think of electricity like a water hose. Voltage is the pressure of the water going through the hose. Current, measured in amperes, is the flow of electrons. It's like the diameter of the hose, and resistance is anything that opposes that flow, like sand in the hose that slows down water flow. Transformers work only with alternating current AC. That's because you need constantly changing magnetic field to induce voltage, and AC provides that naturally. In the US, we use 60 Hertz, which means the current changes direction 60 times per second. And while homes usually run on single-phase power, most industrial sites use three-phase power. Three-phase delivers power more smoothly, reduces losses, and allows smaller, more efficient motors and equipment. Here's the step-by-step. An AC source feeds the primary winding. That current creates a changing magnetic field, also called magnetic flux. The iron core channels that flux so it interacts efficiently with the secondary winding. The secondary winding, electrically isolated from the first, picks up that changing magnetic field. Faraday's law tells us that this induces a voltage in the secondary. The number of turns in the coils determines whether the voltage goes up or down. Finally, you connect a load to the secondary and the transformer delivers the right voltage, all without the two circuits ever touching directly. One question we get all the time is, why step up voltage in the first place? Think about moving power hundreds of miles from a wind farm to a city. If voltage stays low, current has to be high. High current means more resistance, which means more heat, wasted energy. By stepping up the voltage, we lower current, reduce resistant losses, and make long-distance transmission practical. So that's the foundation. Transformers step voltage up or down, using electromagnetic induction to move energy efficiently from one point to another. This simple but powerful principle is what keeps the entire grid running, from massive industrial sites down to the toaster in your kitchen. At Giga, we design and build transformers for every application, so you always get the right voltage, the right performance, and the right support for your project.